Hello, welcome to the chapter on thermodynamics. This is the second part of thermodynamics. We talk about free energy and entropy. So this is kind of a made-up thing. This is the book's intro. So you see the water and it flows this way and goes down here, and this is one of those things that can't actually happen. So this is one of the ideas of perpetual motion. Perpetual motion can't happen because of heat tax. So because of entropy. So before I talk about perpetual motion, let me talk about how we generate electricity. So uh, we have a flame, some heat, and we have a boiler, and then the steam runs in terms of turbine. So the way a turbine works, you have a wire, and you have well, a turbine is a fan, so the steam comes in and it turns the fan. We talked a little bit about the dry steam, the superheated steam, and then it runs a generator. Generator is just something that spins around a wire that induces a current flow, and then electricity goes along the high tension wires to your house, and then goes to your stove or whatever it is you're running. So the question is, does all the energy from the flame go to the water? And the answer is no, of course not. Is all the energy on the turbine, is that transferred from the steam? There is some heat loss. There's friction along the gears of the turbine. Generator, same thing. The high tension wires, there's energy loss of the electricity going through the high tension wires, and then as all the energy finally gets to the home, when you use electricity, is it all being used to boil water or whatever it is, running your TV? No, there's energy losses everywhere. So all of that's the heat tax and entropy. Here is typical load profile for Oahu. The y-axis is the number of megawatts, and then the time. And you can see, well, what's weird about Hawaii is that our peak hours are between 6 and 9 p.m. So actually, that's when we use our most electricity. And the problems is solar power. Solar power works best during the day. And what I've written in blue there, that's typically the load profile for everywhere else. Is you have a base load profile, and then you have the peak hours, usually between 8 and 5 on most places. Here in Hawaii, I said it's 6 to 9, although you can see we do have a fairly decent load throughout the day. And then we have baseline. Baseline's important because we like having things always on, things like traffic lights and refrigeration for food, and hospitals. Hospitals are always running. Emergency services, telecommunications, these things are always on. Uh, so uh, when whenever there is loss of power, one of the things that always requests for power are the refrigerators for fish. Because of the storing the fish, all the fish will spoil. So that's uh, food security is important. So they have backup generators as well. So and hospitals also have backup generators in case the power goes down. So there's all sorts of things. So uh, Hawaii is unique in that regards. And so let's look at wind energy. So one of the problems with wind energy is trying to figure out if it's useful or not. So this is the generation that has a combined capacity of 2,800 megawatts. On that red line there is 2,800 megawatts. How often does it actually reach that capacity? It rarely ever does, a couple hours per year. You can see this is a problem with wind energy, is that it frequently goes to zero, which makes it hard to be usable in a grid. And here is and this is in Canada. These are data taken in Canada, and this is a just a regular load profile. In Canada, that you have the energy users there, so it never goes off, and there's a peak during the day and then the low point at night. Medium wind, you can see here, there's quite a bit when it hits zero, and high wind, that's a high wind situation. High wind is actually really bad for wind farms. It's too gusty, and you get it's less useful than the medium wind. Low wind is actually the best. Low wind is the slow and steady wind. So where does all this energy go? I mean, well, it goes in the grid, and we get surges and valleys in the grid. So there has to be something to back that up, and it's typically a natural gas turbine is what is used, and so then the natural gas turbine needs to be run. But with wind energy, they're like, well, how do we turn wind energy into something useful? And they think, oh, okay, well, what if we use wind energy to pump water uphill and then just use the water on a turbine? Because hydroelectric is great. It's steady. They're small, so let's do that. And then the energy loss from it was just too much. And like, well, what if we turn um, wind energy into hydrogen and oxygen? We'll crack water into hydrogen and oxygen, and that's good too. But the problem is that water is 89% oxygen, so it's not very it's not as useful per se. It's just it's I mean, it's great. It puts more oxygen in the atmosphere, but also you're not getting as much hydrogen out of it. So it's an economic question. So here are that's Canada. Here's some data from Hawaii. So you can see here in Southport and the Big Island that there's peaks and valleys and the gusts. Same thing with Bellows Air Force Base on Oahu. So the point of this is that as we're looking for alternative energies, one of the problems that we have is just good old thermodynamics. And well, it's hard to. It's like, oh, we should just use lots of alternative energy. Well, the reason why we use fossil fuels as sources because they're consistent. And as we look for things like solar and wind, it's just they're inconsistent, and we need to have a baseline. So how are we going to do that? Those are for future discussions for future classes. But a lot of this happens in thermo. So let's talk about thermo. Limits of thermo. So you can't tell. You can only tell what the end products are, not how quickly it will react. So, for instance, my brother, he has a wedding ring. In his wedding ring, he has gold attached to platinum. And I told him one time, I was like, that ring is going to corrode eventually because of the galvanic cell from platinum and gold. He goes, well, how long is that going to take? I was like, oh, a couple hundred years. And he goes, all right, that's fine. He's like, I can tell you that the platinum will cause the gold to corrode, but I can't tell you how fast. I mean, well, I did tell you it was a couple hundred years. But we know that it'll happen. Same thing with diamonds. So at this temperature and pressure, diamonds are not forever. They will slowly turn back to graphite. But it'll take a long time, on the order of millions of years. So, and given that human civilization is only a couple thousand years old, millions of years does seem like forever. Certainly within like most of my family's recollection. I mean, I only know back to 4 generations. And so anyways, then spontaneous. So, okay, so some reactions and processes are spontaneous, just like spontaneous people. A spontaneous person, the person's always crazy, like, oh, I'm going to go jump on the waterfall, isn't it fun? Oh, I'm going to go skydiving tomorrow, you want to come with me? That's a spontaneous person. So iron rusting, that's spontaneous. You can get something non-spontaneous to happen, but you have to bribe it with energy. So you can turn rust into iron. And we do that. That's how we crack ore. But it's just like a non-spontaneous person. Like, come on, let's go out. Let's go out for ice cream. You like ice cream? No, you don't want to go to ice cream. What if I buy you ice cream? Will you come out with me? And then that's you're kind of having to cajole the person, the non-spontaneous person, give that person what he or she wants. Same thing with a chemical reaction or process. So rust turning to iron, you can make it happen. You just got to hit it with you got to reduce it with carbon and hit it with a lot of energy. And there are some endothermic reactions that happen, like ice melting. Ice melting is an endothermic process. Why does this happen? So the reason why is because of entropy. And we talk a little bit about entropy when we talk about solutions, but entropy, it's the measure of disorder. It's the number of energy equivalent ways to achieve a particular state. So the higher the achievable ways, the higher the entropy, the more probability it is to happen. To give you a little bit of history, a lot of people still believe in fate, and thought that the universe was a beautifully calculated and created thing, and physics was being researched, studied, like, oh, okay, if we know where we're at and where we're going, we'll just know everything. And then as this went on, they figured out, like, oh, one of the things that runs the universe is probability. It's just plain old chance and probability. And that was a big shock to a lot of people, that this entropy, which is just probability, is what drives many, many things. And then it became a fearful thing in the 70s because of the heat death of the universe, saying eventually entropy will take over and the universe will just be a dead, sparse place, and people will get really upset about that. And now we have dark energy, which is making the universe expand faster, which negates that argument. And now we're worried about the big rip, where the universe is going so fast that it can rip apart space-time itself. So we're, different doomsday for a different time. I guess I don't know what the next doomsday scenario is going to be. But okay, so this is entropy. Entropy has two definitions. Entropy is calculable by the Boltzmann constant and then times the natural log of the number of states. And it is also defined as a reversible heat transfer over temperature. So, which tells you something: if there's no heat transfer, there's no change in entropy. So some things that are adiabatic or no heat transfer means they're isentropic or same entropy as well. So let's talk about these microstates. So if you have this condition where you have just 4 molecules of gas and then you have 2 tubes, how likely is it to find all the gas in one tube? It's not nearly as likely as having this scenario over here where it's evenly spread. So having all the gas in one tube, there's just 2 chances that's going to happen. And here there are 6 chances, so it's 3 times more likely to have an even split between the gases. So this one on the right, this is more entropy favored. So this is just 4 gas molecules. What if we have a big number, like, I don't know, 6 times 10 to the 23rd? Are they going to be evenly spaced? Of course they are. It's going to be, the probability of that is so large, you're not going to find all the gas concentrated in one spot. So let's look at this. Which one of these has a positive change in entropy? So entropy increasing. So we have A here, we have it concentrated in the far left box, and then we have it diluted in all the box. Entropy is positive there, so entropy is increasing. For part B, we have a very diffuse situation going to a very concentrated situation. That's also false. That entropy is going down in B. In C, we have, although the middle box has 4, there's 2 single in each of the ones. That's more dilute than having all of them, having the concentrated in one of the box. So entropy is going down there. So the only one where entropy is increasing is the first one, A. Okay, so let's do a quick review of some things with thermo. System and surroundings. Would you pick your system to make your math easiest? And so we'll talk a little bit about some of the math that we go through, but in the end, you pick your system typically off of its compounder conditions to make the math easiest, and the surroundings is just the rest of the universe. And the change in entropy is the final minus the initial, and the entropy change for the universe is the entropy change of the system plus the entropy change of the surroundings. So we have the second law of thermodynamics, which says entropy of the universe is always increasing. Well, it's greater than or equal to 0. How can you have the entropy change be equal to 0 if there's no heat transfer? If there's no heat transfer, there will be entropy change of 0. But that's for the whole universe. The heat transfer doesn't stop for the universe. It's always going. Stars are still burning. People are still bringing ice cream out of the freezers, right? Ice is melting, these types of things. Or water is condensing. So somewhere there, the entropy in the universe is increasing. And we have an equation here. The change in entropy of the surroundings, S is entropy if you haven't picked up here. Change in entropy of the surroundings is minus the change in enthalpy for the system over the temperature. And another thing to note, the number of moles of gases. So if we have SO2 gas plus Cl2 gas to make SO2 Cl2 gas, so 2 moles of gas combined to 1 mole of gas, the number of moles of gas goes down, entropy also goes down. The other direction, 1 mole of gas breaking apart to form 2 moles of gas, entropy is increasing for that process. Here we have calcium carbonate going into carbon dioxide and calcium oxide. We're generating a mole of gas. Entropy is increasing in this. Okay, so let's use this to solve a problem. So we have propane plus 5 oxygens makes 3 CO2 and 4 waters. The heat of reaction is minus 2044 kilojoules. Calculate the entropy change of surroundings with this reaction at 25 degrees. So this is the delta S surroundings is the equation written above. It's minus delta H over T, which is minus and minus 2044 times 10 to the third joules, so kilojoules, over 298 Kelvin. So there you go. I forgot to grab my calculator. Okay, throwing on my calculator, I get positive 2859 joules per Kelvin. So joules per Kelvin are the units for entropy. Determine for the sign for energy change for entropy change for the system. So B, we have 6 moles of gas going to 7 moles of gas. Entropy, that because we're increasing the number of moles of gas, entropy change is positive. Determine the entropy change for the universe. So C, C is ugly. So we have delta S universe is delta S the system and delta S the surroundings. So this is a positive number plus a positive number, so entropy change for the universe is a positive number. So because of that, this will be spontaneous. For these though, you can only, what would you do if one was negative, say the entropy delta S the surroundings is negative, or the entropy change the system was negative and one was positive? Which one? You don't have to worry about an ambiguous thing here. I'm not going to test you on something like that. Okay. Let's see if you can figure this out. We have this equation with this delta H. What is the change in entropy for the surroundings at 25 degrees Celsius, 298 K? Why don't you try this out? So hopefully you got that result for this one. Okay, so join me next time to further your discussion on entropy. Goodbye for now.